The US Department of Defense continues to push for the use of open architecture solutions as a means to get better avionics hardware into the field more quickly and at lower cost. Major defense suppliers like Bell have embraced the Modular Open System Approach to enable quick, cost-effective new technology integration. In this video, we will explain how Rapita works with companies like Bell and other ecosystem partners like DDC-I and North Atlantic Industries to facilitate compliance with the Future Airborne Capability Environment, or FACE standard. Founded in 2010 to develop an open architecture technical standard, as well as business models for implementing FACE standards in systems. The purpose of the FACE standard is to provide a reference architecture based on segments, which can be composed to meet the final system requirements. FACE provides the logical interfaces between these segments to allow for portability and reuse. The operating system segment, or OSS, provides a foundation to the other segments and thus is shown above the others in the diagram. The FACE standard builds on existing standards. In the case of the OSS bundle, it builds on the POSIX and ARINC 653 standards. Avionics system designers and integrators designing to the FACE standard under the safety, safety extended, or security profiles must include an ARINC 653 partitioned operating environment in their architecture. Assuring partitioning on a unicore is challenging, but largely a solved problem. Assuring partitioning on a multicore system is much more difficult. The use of an ARINC 653 compliant RTOS like DDC-I's DOS meets a FACE requirement and implies partitioning is achieved. However, these advanced RTOS technologies are not sufficient in themselves to prove the partitioning is robust. The AMC 2193 standard sets out specific objectives which need to be satisfied when designing multi-core systems according to DO-178C guidance. FAA guidance has often been adopted by US military airworthiness authorities, and AMC 2193 is no exception. AMC 2193 documentation extends the partitioning concept for multi-core processors, with specific reference to providing evidence that partitioning is robust. In a multi-core system, multiple applications can now run simultaneously, each on their own core. Some resources are private and exclusive to a single core, such as the L1 cache, as shown in this example. However, other resources are shared, such as the L2 cache, main memory and I/O devices. The applications on different cores can thus contend for access to these shared resources, impact each other's performance, and down the isolation between partitions. Only recently have early adopters attempted to use all cores with a mixed criticality of software by following the guidance in DO-297 and AMC 2193. This approach is complex, with independent applications running within the same partition window on separate cores, despite the applications being certified at different design assurance levels. In this case, independent partitions with different criticality are able to run simultaneously on different cores, within the same minor time frame of the schedule. Independent partitions running on distinct cores now compete for shared resources. That contention can cause delays, thus increasing the software's worst-case execution time. Mitigation of multi-core interference requires that partitions be isolated from each other. Some isolation mechanisms are provided by a multi-core RTOS like VxWorks 653 Multicore Edition. Such RTOSs can manage processor cores, ensuring the usage of any one application is deterministically bounded within its partition. Verification that multi-core interference channels have been mitigated is an essential step in meeting AMC 2193 objectives. Rapita have developed their MAC 178 solution to help meet those objectives via a combination of advanced tooling and engineering services. The Rapita approach to multi-core timing analysis uses two phases within a test methodology for measuring multi-core interference channels. The first phase is platform characterization, wherein the platform is defined as both the computational hardware as well as the RTOS. In this phase, we check the outer bounds of possible multi-core interference by competing rapidemons against each other on all cores. RAPI-daemons are applications that create targeted interference on shared resources. Because RAPI-daemons are tuned to stress a single targeted shared resource, this provides a signature of the performance possible when cores compete continuously for that resource. This phase can be done even before application software is available. The second phase is software characterization. Individual software applications intended for use in flight are first measured running alone on a core, while the other cores are dormant, providing a baseline measurement of the software timing behavior. Next, we measure the increase in worst-case execution time in the presence of RAPI-daemon adversaries running on the other cores. By comparing the worst-case execution time with and without the RAPI-daemons running, we can quantify worst-case multicore interference. This can be measured against system requirements. Rapita have designed MAC178 to work seamlessly with integrated modular avionics, or IMA, workflows. Using the Rapita solution, suppliers and system integrators can accumulate certification artifacts over the course of several independent verification efforts. Even with the incremental verification benefits, the complexity and number of interference channels in a multi-core avionics system require a large number of tests. Thus, tool automation is important to keep the schedule and cost of verification reasonably constrained. The Rapita approach automates key stages of the workflow, using both RAPI-daemon interference generators and the Rapita verification suite tools. If you would like to learn more about how Rapita Systems and our ecosystem partners can help you build and verify your FACE platform, please use the contact options here.